Hello, my name is Edward Jin, and this is my fourth and final lab presentation in Physics 2211 titled Oscillation. The purpose of this experiment is to examine the motion of a mass oscillating vertically on a spring and compare both experimental and computational models concerning the energy principle. The experimental data model will be analyzed using the Tracker app, and the computational model will be created with GlowScript code. Newton's second law is used, and it states that an object's acceleration depends on the net force applied to it and its mass. Potential energy, which is a new concept in this lab, is the energy stored in an object due to its position. Since we are using a point particle system, the mass has no internal energy, which will be useful for our lab presentation. Here are some key principles and formulas, which include Newton's second law and the energy principle. For Newton's second law, we use the velocity and position update formulas, force equals mass times acceleration, and the net force formula. For the energy principle, also known as the law of conservation of energy, we examine how the change in energy equals work, considering kinetic energy, gravitational energy, and spring potential energy. The energy principle shows that the energy is neither created nor destroyed. Using the provided pre-lecture video, we determined our system as the spring, mass, earth, and nothing in the surroundings. Initially, the mass and spring are motionless, resulting in zero velocity and net force. The mass is 0.402 kilograms, and the spring constant is 6.83 Newton meters. Using the spring force equation, we've found that the relaxed length of the spring to be 0.123 meters. With the Tracker app, I recorded the X and Y positions of the mass during the video, and then copied this data into Microsoft Excel and turned it into a CSV file to use in the computational model. Here's the data and graphs from my experiment. Here we set initial conditions in our code, including the mass of the system, spring constant, gravitational force, relaxed spring length, and the ball's initial position and velocity. Using previous formulas and constants, we calculated both energy and model position in the x and y directions. We applied Newton's second law for position and velocity update formulas and calculated the final energy at each mass position. The results from the energy graph support the energy principle, showing that total energy, the orange line, remains constant since there are no surroundings, while the other three values are oscillating. As the mass slows down over time, the kinetic energy decreases, which is consistent with the graph showing decreasing peaks and troughs. The spring potential and gravitational potential energies are inversely related, oscillating in opposite directions. My observed position model closely matches the computational model for the x position. However, for the y position versus time, the model differs slightly at each time value, though they follow similar trends. This discrepancy could be due to human error in using the Tracker app or tracking the mass's motion. Regarding the first discussion question, I believe the GlowScript generated graph shows the energy principle is satisfied with the total sum of energy being zero throughout the entire experiment. Since the sum of the energy stayed at a constant zero, this shows that the computational model reflects the physical behavior of an oscillating spring system. Regarding the second discussion question, I observed that the time differences between two minimum or maximums on the graph differ because the mass moves like a spring in the y direction and a pendulum in the x direction. In conclusion, the experiment's purpose was achieved as we observed the motion of a mass oscillating vertically on a spring and related it through both experimental and computational models. Thank you.